Fine.
Great, great.
Yes.
So Nabamita is also here. Hi, Nabamita, can you hear and see me?
Yeah, I can see you and I can hear you.
Lovely. So Nabamita is the session chair, so she's the boss. She's going to tell us what to do, when to do, and we are beginning in 7 minutes from now. That's the only
All right.
topic. Yeah. Okay. All right. So Nabamita, you may
Laura,
take
just
over.
usually there are lots of questions. So is it okay? I will ask the participants that if some questions are really necessary to be answered in between the talk, then can they stop you and ask questions?
During the talk?
Yes.
Yes, yes, that would be great. It's better. Yeah.
Okay. I will request them that if the question can be deferred till the end of the talk, then they will do that. Okay. So we will roughly go as like 15 minutes of talks and then 10 minutes of questions.
Okay, okay. Yeah, I don't mind if they interrupt me during the talk. It's always good.
Thank you.
Sure.
So if I understand, then right now you are in Vienna, right?
Yes, that's right. Yeah, yes. I'm at the Technical University of Vienna. There are actually two. So one is called the University of Vienna, and is their historical one, and the one I'm at is the Technical University, which is more focused on sciences, engineer and stuff. But they are very close from each other, like they are both in the center. And yes, so in my group there is, well, in the group where I am, there is Daniel Grumiller and people working on gravity, also Anton Reba and more. That's
in postdoc, right?
Actually I'm an assistant professor as us after tomorrow. But you couldn't know, but yes. But I joined there as a postdoc. With
Thank God you told me. I was just going to tell that you are a postdoc. Thanks.
No, I mean it's factually true. I mean, so yeah. You let me know whenever you will want me to share a screen. I will. I will just need to to switch this diaporama because it will take me a few seconds. But
I think you can actually share your screens. I mean, we are like just 3 minutes away from beginning.
Okay.
Yeah. Okay.
Great. Right. So there it is, and then okay. So I should try to make it fit in 50 minutes, right? That's what you said.
Yeah, I mean, I hope you would not be interrupted a lot in between the talk. But yeah, I mean, it's okay if you overgo by 5 minutes. That's fine. It's not an issue.
Okay, yes. If I'm not interrupted, I will really try to keep it into 50 minutes. Otherwise, you will forgive me.
It's okay. Just to help you a bit, I will let you know 10 minutes in advance. So when it would be around 45 minutes, I'll tell you that we are at 45
Okay.
minutes.
Sounds
Just
good.
to give you an idea. Because when I give a talk, I generally never have an idea for how long I'm speaking.
Yes, yes.
Okay, so Alok, shall we begin?
Oh, yes, please. Please go ahead.
Thanks, Alok. So we are extremely happy to have Laura Donnay from TU Vienna today joining us for our second review talk in ISM. I have followed Laura's work from when she was a graduate student, and she has done extremely good work on flat space holography. And I'm really happy to have her here today. Laura, please go ahead.
Thank you very much. Thank you for your kind words. And I would like to thank all the organizers for the invitation to present this review talk on this program, which is called Celestial Holography, which proposes a holographic duality for quantum gravity in asymptotically flat spacetimes in terms of a theory which is still to be discovered, but that goes under the name of a celestial conformal field theory that lives on the sphere at infinity. So the motivation, or my personal motivation for this program, and in general for physics, it has to do with black holes, as it's a fact that black holes are compelling us to reconsider the fundamental laws of nature and are keen on our understanding of quantum gravity. And I think it's fair to say that the spectacular advances that have been made in understanding these amazing objects in our universe goes hand in hand with the holographic principle. The holographic principle proposes that a theory of quantum gravity is actually encoded in a different theory that does not involve gravity and lives in a lower dimensional spacetime. And we would like to understand how general this principle is. And to do that, we need to go beyond the canonical cases. Indeed, the most concrete realization of this principle is, as you know, given by the anti-de Sitter conformal field theory correspondence, which holds for spacetime which are anti-de Sitter, namely with a negative cosmological constant. Now, the purpose of the program that I will present now is to extend this paradigm for spacetime which are asymptotically flat, namely which have zero cosmological constant. Of course, we know that we live in a de Sitter spacetime with a positive cosmological constant, but zero lambda is an excellent approximation for physics, from collider physics to astrophysical scales, smaller than cosmological scales. So this will be the focus of this review talk. And in particular, we would like to understand whether there is a sense in which quantum gravity in flat spacetime accepts a holographic dual theory, where this theory live and what are its properties. So as I said, in the last years has emerged a program which is called celestial holography, which proposes a concrete realization for what it means to be, for quantum gravity to be holographic in asymptotically flat spacetime. And this program has been motivated by a lot of work and discoveries about the infrastructure of gravity and gauge theory that I will try to review. So this will be basically the plan of the talk will be to review these features, and before I dive it into the core of celestial holography. So I want to say that you're very welcome to interrupt me at any moment to ask questions or make comments. So the roadmap that I will use for this presentation has to do with symmetries. As we know, symmetries is always a good idea to look at the symmetry of a problem. And if one think of this as being really the prime principle that we want to follow, a very first question one should ask before diving into even trying to understand holography is, what are the symmetries of asymptotically flat spacetimes? And surprisingly, this question is not yet answered fully there actually. But it was partially answered in the very old works of people in general relativity in the 60s that I want to present, because this is really at the core of celestial holography. So let me do that. So I will first introduce my conventions for coordinate systems and so on. So here I've written just starting with exactly flat or Minkowski metric in 4 space-time dimensions, which is described in terms of these coordinates, sometimes called Bondi coordinates, where you can see that it involves the time. Here, u is a retarded time. It's basically t minus r. R is a radial coordinate. And I will use, instead of the usual theta and phi angles for the round sphere, these complex or stereographic coordinates z and z bar. In terms of this coordinate, the round sphere metric takes this form. So a very important diagram in this talk will be the Penrose diagram of Minkowski space, where the space-time has been compactified and the causal structure preserved. So the boundary of Minkowski space is called this future null infinity, which is this null hypersurface denoted by this letter scri plus, which is the boundary that you go to when you take this retarded time constant and take the radial distance very big. Now in this diagram, massless particle always propagate along lines of 45 degrees. So future null infinity is the location where all massless particles end their life. Each point in this diagram is actually a two-sphere labeled by these angles z and z bar. Similarly, there is a past null infinity where all massless particles come from, and the boundary of Minkowski space is given so by this real line spanned by the time coordinate u times a sphere, a two-sphere, which is called the celestial sphere. So the celestial sphere, the asymptotic sphere at the boundary of flat space-time, and will play a very important role in this talk. So now we would like to understand not exactly purely flat Minkowski metric, but what people have called asymptotically flat spacetimes, which are spacetime which have a curvature but which look like Minkowski in the first approximation. And the deviation from the Minkowski line element is given by boundary condition for the metric. So in first approximation, this is just Minkowski space plus some correction, which it's a 1 over R expansion, which involve a bunch of a function here that I will recall. So this function in blue here are arbitrary function of the retarded time and the angles. And this MB function is called the boundary mass aspect. It's an arbitrary function of u z bar, which roughly speaking encodes the energy of the system. Similarly, so if you take a curved black hole, MB will just be a constant. It will be the mass of the black hole. Now, NZ is the angular momentum aspect. And very importantly, this function here, C, is called the asymptotic shear or gravitational data, indicates the presence of gravitational radiation. More precisely, if the time derivative of this function is non-zero, it means that the system you are describing is emitting gravitational radiation, like for instance, black hole merger will emit gravitational wave. This wave will propagate and exit space-time at future null infinity, and you will be able to measure this by this quantity. So this asymptotically flat space-time written like that describes space-time which are emitting radiation. Now, a very prime question is, what is the symmetric group of these kind of space-times? And what you might expect, or what was expected, was actually to recover the Poincaré group, which is the isometric group of Minkowski space, given by 4 translations and 6 Lorentz transformations. What was found indeed, it was a very big surprise in the general relativity community, is instead the so-called BMS group, standing from Bondi, Messner, and Sachs, which is an infinite dimensional extension of the Poincaré group. So how does this infinite dimensional extension appear? Well, what you do when you look at asymptotic symmetries is you're really looking for vector fields which preserve this asymptotic expansion. So what it means is that the rules of the game is that you're allowed to change this function in blue here, but you are not allowed to change the powers in R in the expansion. There is also some gauge fixing at play, but I will not enter into too much subtleties. But when you do that, you find that the following vector fields, which is called a super translation vector field, preserve this form of metric. And the important thing about this vector field that it involves an arbitrary function f of the angles. And because this function f is arbitrary, basically you are allowed to shift the retarded time by an infinite amount of functions instead of the usual translation where you just shift by a constant. So that means that you have an infinite amount of freedom of doing so. That's why the BMS group is an infinite dimensional extension of the Poincaré group. So that's the very first important conclusion, is that the symmetry group of asymptotically flat spacetime is much bigger than the one of Minkowski space. And this infinite dimensional extension of Poincaré is called the BMS group. Yes, is there a question? No, probably there was a microphone. All right. So you see that because you have a boundary in the spacetime, that you have a symmetry enhancement phenomenon, which we are familiar. If you think of ADS3, the symmetry group is the infinite dimensional Virasoro, two-dimensional copy, 2 copies of the Virasoro symmetry. Here is an analogous phenomenon for flat spacetime. And let me point out that the symmetry were originally totally disregarded. More than that, if you look at the paper from Sachs in the 60s, people were very annoyed by this. They really wanted to recover the Poincaré group. And they say, you see that I told you that the feature of supertranslation is that there involves an arbitrary function of the angles. Sachs were saying, you see, it's pretty annoying that we have this function. So we have been trying to kill this function to impose other kind of boundary condition for the metric so that the group reduces to Poincaré. But they were kind of honest in the sense that they said, we tried to kill the symmetry, but we have failed to do so. And really, they didn't know what to do with this symmetry. But as Zach said, maybe the fact that there is super translation is actually a blessing in disguise, and the stories is actually more interesting than what we could have expected. And indeed, the presence of these symmetries is actually has played a fundamental role in understanding the infrared structure of gravity and gauge theories. And to show you that, let me recall this story that was first pointed out by Andy Strominger a couple of years ago, is that the symmetries are actually the imprint of soft theorems in quantum field theory. Soft theorems are statements about amplitudes which involve what is called a soft particle, namely a particle which have zero energy. So here you have, say, an amplitude with n particle, a scattering amplitude with n particle. You add an extra particle which has zero energy, which is called soft. And the soft theorems is a statement that this amplitude will factorize, namely will be given by the amplitude without the soft insertion times a factor here called the soft factor, which has here a pole in 1/omega. So this is something studied by Weinberg and other people in quantum field theory. So a priori has nothing to do with general relativity. But what you can actually see is that the leading soft graviton theorem has a symmetry interpretation, and indeed is nothing but the word identity, which is associated to supertranslation symmetry. So there is a precise mathematical statement to show that this theorem arises from this word identity involving the Noether charge associated to supertranslation symmetry spanned by the function f here. There are a couple of steps involved that I don't want to develop, but there is really a precise mathematical statement. And actually, the story is even richer than that because, and this goes under the name of so-called infrared triangle developed by Strominger and collaborators, which establishes a set of relationship between these three topics in physics. The first one, this asymptotic symmetry, is this statement about infinite dimensional enhancement in general relativity. And the second one is this soft theorems in quantum field theory. And very remarkably, there is also an observational imprint of these features, which is known as the memory effect. So the memory effect is something that was predicted just from looking at Einstein's equation by these people in the 70s, and is the fact that detectors which detect gravitational waves will undergo a permanent relative displacement long after the gravitational wave has passed. So this is, for instance, the signal that in red that you will get, how you would measure these effects. For instance, if you have a signal at LIGO, you will see that long after the wave has passed, there will be a residual net displacement that you can measure, and it's expected, this effect is expected to be measured in the next couple of years at LIGO or LISA. So you have this very beautiful set of relationships, and this carries on not only for gravity, but also for gauge theories in different amount of space-time dimensions. So it's supposed to be a very fundamental feature of the infrared structure of gauge theory and gravity. And this was at the core of the celestial holography program that I want to present, if there is no question at this stage.
Yeah, I don't see any question. Please go
Okay,
ahead.
great.
Could I ask briefly? Sorry.
Sure.
Yeah. When we study ADS, we allow for boundary conditions that are more general than normalizable states. We allow for non-normalizable deformations, which then have some interpretation, right? Deforming by operators. So I was wondering whether there is something like the analog of a non-normalizable deformation of your boundary conditions. something that is not some finite energy kind of space-time, but is of interest anyway for some reason.
Yes, actually, this is a very important feature, actually, because one of the question that you might ask is, what is the analog of the BMS symmetry for AD? I mean, how come that, you could think that you might want to see these symmetries or this feature of a flat space-time coming from, let's say, a large ADS radius limit of the story in ADS, and typically, I mean, this is a long story, so maybe I want to expand too much on that, but there has been some effort trying to precisely understand which kind of boundary condition in ADS you need to impose. So you will need to allow for fluxes of outgoing radiation, and strongly relaxing these boundary conditions will give you some sort of BMS symmetry in the limit. So this and the non-normalizability of the state is tightly connected to that. So, but I think it's very interesting to always try to relate what we know from ADS and see how the story goes on from flat space-time. And the story is very subtle and it's a long story, but yeah, I hope I more or less answer the question. If there is no other question, we can come back to that in the discussion.
Is there any relationship between large diffeomorphisms and the BMS group, like the large gauge transformations?
Yes, so BMS symmetries are large, what people call large diffeomorphisms, in the sense that they have there are many ways to express this statement. One way is to say that they have a non-zero charge associated to them, this Noether charge that is non-zero at the boundary, or you can say that the asymptotic symmetry parameter is not zero when at the boundary, but yes, this is precisely how people have called them sometimes non-proper transformations, and so this is precisely what they are.
Could they be the coset of the large diffeomorphisms with the small diffeomorphisms?
Yeah, so this is another way of saying, so you basically two approach, either you look at what is called residual gauge transformations or diffeomorphisms, which are the thing you obtain by first starting to fix the gauge. Here I was working in bounded gauge, but you might think of other kind of gauges, or you look at the quotient of the so-called asymptotic symmetry mod out by the trivial ones, and these are eventually leading to the same result. But yes, these are two different ways of defining these large gauge transformations.
Thanks.
Okay, thanks for the question. So now let's go into the core of the celestial holography. So a very prime observation is that, so here I've rewritten again our Penrose diagram, is that the four-dimensional Lorentz groups act on the celestial sphere on this coordinate Z and Z bar as the two-dimensional conformal group. This is just a statement, a fact about symmetries. So this is just the Möbius transformation on Z, and there is an analogous thing on Z bar. So somehow, by construction, if you go to a boost eigenstate basis, you will have that object will naturally transform as 2D conformal with 2D conformal properties. And this is indeed what is at the core of celestial holography. So more precisely, this is a statement that the four-dimensional space-time S matrix can be encoded in a theory that we will call a celestial conformal field theory. So the word celestial is there for two purposes. Basically, the first one is to tell you that it lives on the celestial sphere. So this is the asymptotic two-dimensional sphere at infinity. And the word is also there to indicate that, as you will see, there are many features of this theory which are unconventional compared to usual CFT. So to which extent this thing is actually differ from a usual 2D CFT is actually one of the main challenges of the program, and people are actively working on that. But so let's take this idea seriously and let's see how far we can go. Namely, can we what happens if we recast the scattering elements of the S matrix in 4D quantum gravity in terms of a correlation function? So this is a correlation function in this 2D celestial CFT, which involve a bunch of operators, which will be labeled by the point Z and Z bar at which the particle enters or exists spacetimes, and a bunch of quantum numbers, namely their conformally dimension, their spin. So you can actually, because of the symmetry observation I mentioned before, if you work in a boost basis, you will have that naturally the object will transform with some sort of conformal property. So this motivated the use of these bases, which I call the holographic basis, which involves, so crucial in this program, there is this integral transform, which is called the Mellin transform, which is a Mellin transform of the energy of the particle. So if you have a plane wave, so here I will focus on massless, on the massless case. There is an analogous story for massive states. I'm not presenting that because I don't have time, but you can think that this story mutatis mutandis carries through for massive states. But let me focus on massless case. So you can parameterize their null momentum P mu in terms of their energy and the point Z at Z bar at which the particle is pointing is heading to. So again, I recall that each massless particle will pierce the celestial sphere at the point Z and Z bar. Now, if you do this Mellin transform, very remarkably, the nice thing about that is that now the object you will get, which I call O here, will now not depend any longer of the energy, but now will depend of this delta, which is a conformal dimension, as indeed this object now transform manifestly under SL2C as a primaries of weights H and H bar, which are respectively the sum and differences of the dimension, the spin. So here this was for a massless object, but if you have spin, you will have a 4-dimensional helicity factor in front of that. And the 2D spin is simply identified with the 4-dimensional helicity. So this is just to say that we will work in a basis which makes the conformal transformation of the asymptotic state manifest. The price to pay is that now the translation symmetry will be obscured because of this Mellin integral. Right, so is there any question about that? If not, I will carry on with the celestial currents. So if not, let me tell you about these currents because they are actually important. So now we will be working with objects which are labeled by weights H and H bar, remembering that they also express in they will also be the point Z and Z bar of the celestial sphere. And very remarkably, what you can construct object which transform as current on the celestial sphere when now you take what we call a conformally soft limits, which is a limit obtained by taking the conformal dimension to take some integer values. Because you see, where was a soft particle? Before a soft particle has omega goes to 0. But now when you work in this new basis, it's no longer clear what you mean by a soft particle, because basically you have traded the energy for a conformal dimension delta. So do you still have a notion of softness to some extent in this on the celestial sphere? And the statement is that yes, And this thing is precisely captured by integer values for the conformal dimension. And so in particular, you can construct currents which transform nicely and encode actually soft theorems in celestial holography. So let's take a spin 1 particle and take the conformalist soft limit delta goes to 1. Then you can see directly from the weights, so delta is 1 and j is 1, that you will have an object which has weights 1, 0. And this object precisely plays the role of a U1 Kac-Moody current on the celestial sphere. And in the insertion of this operator into a correlation function on the celestial sphere is actually encoding precisely Weinberg soft photon theorem. So if you want, there is, I told you before, there was a precise way in which the word identity associated to asymptotic symmetries were in one-to-one with the soft theorems. And here in this basis, we can recover this statement, but using objects which really are currents or conformally soft objects for specific deltas. So this is for QAD. Now for gravity, you have this super translation symmetry is actually pretty subtle to deal with, because if the current that is playing an important role is actually a descendant of the object with delta equal to 1. So it's an object which has 3/2, 1/2. And indeed, the insertion of this super translation current gives you here written in the operator product expansion form, it is encoding the Weinberg's leading soft graviton theorem. And you can see that because we're in this basis, I told you that the translation symmetry is getting a little bit tricky. And indeed, inserting this object amounts to shifting the weights of the operator on the celestial sphere of 1/2 each. So you can see that already now we have some features which are not conventional from the usual CFT perspective. And remarkably, there is another important current in the game, which is the two-dimensional stress tensor. So the stress tensor of the celestial CFT is actually what is called a shadow transform of the conformal primary of weights delta equals 0. So the shadow transform is an integral transform. This is actually just what it is for this case. The shadow transform is typically an integral transform that maps a primaries with weight delta to a new primary with weight 2 minus delta for 2D CFT. And so when you do that to this operator, you will indeed obtain an object which has weight 2, 0. And the operator product expansion of the celestial CFT stress tensor with any operator on the celestial sphere gives you, as expected, precisely the OPE of a stress tensor in a 2D CFT. So this object has a precise, let's say, can be mapped to the object in the gravitational solution space in a kind of intricate way, because this is a non-local is non-local in terms of the gravitational solution space. But it's pretty remarkable that there is a current which is playing the role of a stress tensor. So now this is a summary of the thing I just introduced. So I told you we work in this basis. Objects, the particles will be interpreted as being operators on the celestial sphere, labeled by weights and points on the sphere. And remarkably, we can construct conformally soft. Yes, please.
Hi, sorry to interrupt. Just on the previous slide, you define this T as an integral or transform, the shadow transform of operator O. Now, what is the state which maps to this O?
Yes, so it's just this O is, roughly speaking, is the spin 2 helicity times the Mellin transform of the plane waves, basically. So that's
the graviton.
The graviton, yeah, exactly.
Okay. Nice.
The
Thank you.
graviton, yes, exactly. So all these O's here are up to subtleties, basically Mellin transform of asymptotic states, which are taken to be plane waves and Mellin integrated. Yes.
Okay, thank you.
Is there another question? I see one hand.
Yeah, I have one question. Like, do you have the understanding of the central charge of the CFT? Say, do you have the OP expansion of the two stress tensor?
Yes, yes, thanks for the question. Yes, we do have it. And basically C0, that's just to answer fast. So these, so okay, let me say something. It's like, so people have been computed the OPE of T with T in different ways. I will come back to the when I will present celestial OPs, but basically what you can do is that you can, Stieberger and Taylor have looked at OPE of T with T by taking, what you need to do is you need to take, of course, two conformally self-limits, because you have two stress tensors, and you need also to take a collinear limit. I will talk about that later, to obtain the OPE. And they found that the OPE with T is the one you expect with central charge 0 by looking at Einstein. Yes.
Yeah, I expect that possibly one can read out these things starting from double soft graviton theorem, say, when you have two soft gravitons, and like if you take either simultaneous or maybe consecutive, like from there one can extract this OP coefficient of like of two stress tensors, right?
Yes, yes. It's basically,
and you are telling it's 0?
Yeah. Yes, this was found to be 0. Yeah.
Okay.
So at least, yeah, exactly. And as you know, I might mention that, as you surely know, there is in the usual energy momentum basis, there is these ambiguities on how you take consecutive or double soft limit. There was an interesting paper by Dissler, Horn, and others that there is this ambiguity whether which guy you take first, soft first, and so on and so forth. Actually, in this Mellin basis, this holographic basis, this ambiguity is somehow doesn't show up. So you can do the things in a neat way.
Okay, thank you.
Yeah, thanks. But indeed,
So
it's essentially this double soft limit. Yeah.
Does this mean that the entropy, if you calculate the entropy of the celestial sphere, you will see 0 going by the Cardy formula or something?
Well, yeah. So far we don't have any, we don't have any black hole or stuff in that. This is what you have in mind. So far, so what it means is that at least at this classical, semi-classical level, the central charge of this celestial CFT has to be 0. And actually, from it could by somehow if you think of it like, with what could it be? Because in ADS you have this Brown and No central charge, which is basically 3L over 2G, where L is the ADS radius. Here there is no scale to compensate it, so it should somehow be 0 or infinity. And actually you can see that is 0 also from I also worked on that with Romaro Zicconi from Vienna. You can also see it from the algebra, from the BMS algebra. There is a long story behind all that, because there was found that there was a non-trivial two-co cycle between the super translation and super rotations, and there might be other kind of central extensions which appear at other places. Yeah, we can go into that in the discussion session if you want to, because there is another guy which is actually a shadow stress tensor that might have a sort of off-diagonal central charge, but at least the statement is that T with T, as written there, the C is 0. Right. Okay. But this is all very interesting questions and points to make. All right, so yeah, I mean, so these currents, as I said, encode very naturally soft theorem. So they're really the building block of the soft sector of celestial CFT. And let me make some comments that you can actually relate them in very naturally with the object of the solution space, because let's not forget where we come from. We are coming from. In gravity, we have this solution space which encode the notion of asymptotically flat spacetime. We have very concrete things which are Bondi mass aspect, angular momentum aspect, and the shear. And by looking at what we wanted to emphasize, that looking at the so-called fluxes, which are the U integrated of the time derivative of gravitational solution space objects. You can this is actually you can make a precise map between these fluxes and the celestial currents that I have mentioned before. So by definition, these fluxes are also it's a sort of tautological statement. They are the difference of their value at the future null infinity, square plus when U goes to plus infinity. And the difference of that with the objects at the past of future and infinity, namely scribe plus minus. All right, so now there has been very interesting recent work on the idea that actually these currents, so I've mentioned a couple of them for you, but that there is actually an infinite tower of currents for all these values of the conformal high dimension delta. And very nicely, you can, Strominger showed that you can reorganize all this tower of currents by a clever redefinition of the generators in terms of W1 plus infinity algebra. And there is also a beautiful story that was worked out from a twistor space analysis. Because as you can say, so it's obvious that twistor space is a very very natural language to understand all these features, and to some extent Penrose has probably already talked about these things in a different language. So I find it very beautiful that we have, you know, all these sort of different communities and subfields that are now talking to each other basically about the same things, and it's very nice to see a relationship between all that. So I'm not an expert on that, but I found it very nice. So yeah, I mean, basically the main conclusion of this part is that these currents that live on the celestial sphere and how they are organized give you a powerful principle to see how the soft sector of the S matrix is captured, and basically how all these symmetries organize themselves in a nice way. So before I'm almost at the end of what I wanted to say, and I would try to make some general comments. But before that, I have to mention the work, a lot of works that have been done on the amplitude sides. So I'm sorry, I forgot probably a lot of people. This is the field is developing very fast, and it's difficult to keep track of everything that's being going on. But basically, there's been a lot of effort developed on you know, Mellin transforming scattering amplitudes and see that it takes the form of a correlation function, and deduce from that a lot of, try to constrain, you know, from a sort of bottom-up approach, try to see what it implies on what constraint it implies on the dual putative theory. So what you can do is, as I was mentioning briefly before, you can actually see very easily that a collinear limit. So when you take the momenta of two particles to become parallel, then this is actually equivalent to taking the points on the celestial sphere to coincide. So in other words, collinear limits, so for the amplitudes, corresponds to celestial operator product expansion in the celestial CFT. And there has been, and you can either brute force, these things by, Mellin transform the amplitude, taking collinear limits, and see that it gives you, it constrains the OPE coefficients, or you can just also try to see what are the OPE coefficients from symmetry, just from symmetry principles. Low point celestial amplitudes are inherently endowed with kinematic singularities because you have a bunch of delta functions there that remain. And there have been some efforts trying to tame these singularities by using of so-called shadow, light, and twister transforms by several of these people. There's been some work on conformal block expansion, many things to mention, and also on the UV-IR behavior of celestial amplitudes. Because as you could see, because I'm doing this Mellin integral, we are really probing all energies. So celestial amplitude intrinsically involves a mixing between the UV and the IR. And this is very interesting to look at the implication of this statement for the celestial theory. So I'm reaching the end of the talk. So I think I still have few minutes to review.
Yeah, you have time. Go ahead.
Great. Yes. So I mean, really, what I wanted to show is that physics in the different parts is much richer and much less understood than we thought. So there is this BMS symmetries, the supertranslation symmetries. Now I think it's well understood, but there are other kind of symmetries that I didn't really talked about. But now a question is, what is the full symmetries of quantum gravity in asymptotically flat spacetime? And as I said, this question is only partially answered. And celestial holography really aims at putting the symmetry front and center in the program. And it's really by following these symmetries that this program aims at understanding what is the holographic principle for quantum gravity in flat spacetimes in terms of a two-dimensional theory. So independently of holography, I think a lot of people have been very excited about celestial amplitudes, as they are now, we can see that somehow, you might think you might just work in a different basis, but actually it turns out very fruitful, because these celestial amplitudes are showing hidden mathematical structure that you could not see before, and also allow you to understand things from a new perspective, like for instance, these double copy relationships and so on and so forth. So independently of the holography, this is, if you want, a new window into amplitudes. And to me, what I find very interesting about this program is just it is forcing us to address the principle of holography beyond what we know from ADS, because usually in ADS, I mean, we do not allow the escape of gravitation of radiation. We say, ADS act like a box, but I think we do want to understand physical systems which are emitting gravitational waves, and And celestial holography is forcing us to address this question and to allow for outgoing fluxes. And by doing so, you see that you run out to new features about holography. So you have to somehow extend this paradigm to allow for these cases. And in particular, in celestial holography, you have this extra symmetry, that is the super translation symmetry, which have no analog in usual ADS-CFT. And it gives rise to this intriguing feature, for instance, the fact that the symmetry is, is shifting, is shifting the dimension of the operator in the spectrum. And we have to deal with that. There is no way around it. So this raises the question to which extent celestial conformal field theory resemble or differ from the usual CFT, from ADS-CFT. And this way we have to understand. So there are very many things that are left to be done. By the way, I did not cover all aspects, of course, of the program. There are many people working on that. So again, I'm sorry that I had to focus on only certain aspects of that. And let me mention a few challenges that are ahead for this program. So the very first question is actually, what is a celestial CFT? Because I told you how you could somehow build from the bottom up properties or constraints, for instance, coming from these infinite towers of symmetries, coming from the soft sector. But we would want to do more than that, right? We would like to have at least an intrinsic definition of what is a celestial CFT, or at least what are the list of properties that it should obey. Now there is also this very interesting question whether string theory is actually the only consistent theory of quantum gravity in flat space. So far it has been observed that even at tree level, string theory amplitude are sufficiently well behaved in the UV to admit a celestial representation. And it would be very nice to understand what is the precise relationship between the string wall sheet and the celestial CFT. So there have been some recent works on that. But the question is still to be investigated further. And finally, so this was so far just, assembly flat space-time. But of course, I mean, the big picture would be eventually to involve black holes into the game and to see to which extent, or what can celestial holography tell us about black hole formation and evaporation. Is of course the very ambitious question to solve, but this is tightly related to another program that I was personally involved in, which has to do with this black hole soft hair. And basically a very natural question is to understand what are the global forms of the conservation laws in the presence of black holes, which are consistent with all these celestial symmetries. So I'm done, and thank you very much for listening, and I would take any question you have.
Thank you, Laura. It was a wonderful talk. So we really have time. Please go ahead. I can see 𝗦𝗫𝗀𝘀𝗀𝗀, you can ask a question.
Yeah, so I want to go back to that point of getting a zero central charge, because even a Schwarzschild black hole, for instance, is asymptotically flat, right? The space-time is asymptotically flat. So from the celestial point of view, you should be able to see the entropy of the black hole by measuring, for instance, the outgoing radiation, for instance. So you should be able to see some entropy. But if the central charge is zero, does it mean that you don't? I'm really confused about this point. Can you please explain?
Yes, so this is basically, this is a question that, I mean, this would require basically understanding the last point, right? I mean, because there are, all these conservation laws, or for instance, all these things that I was talking about, like these the fact that the celestial CFT has to be consistent with the conservation laws and all this tower of symmetry. Now, in the presence of the black hole, you know, a scry future knifing is no longer a Cauchy surface, and you will have to include the contribution from the horizon, and you will have to rederive. I mean, when the black hole is there, all these it will have to obey all these conservation laws, but you expect that there will be a contribution of the horizon to, say, the charge. Even the classical charges would get a contribution for the black hole horizon. So you will need to, you know, to encapsulate this. And so far, we don't have access to the full story. I mean, you know, I'm not saying that, you know, and to which extent the usual Cardi formula story or cardiology will work. I mean, it's still an open question.
Okay, thanks.
Shiraz, is that you? I
Hello?
cannot. Yeah,
Hello.
please go ahead.
Hi, Laura. Thanks for a very nice talk. So in one of these slides towards the end, you talk about a conform block expansion. So what sort of operators you expect would appear in such an expansion? In particular, is there any special role played by the so-called unitary principal series?
Yes, so I have to say that this is not my work, so I'm not an expert on these things, but indeed all these principal series typically play an important role. Now I know that about this the spectrum of the conformal block is not fully yet understood. As far as I know, there might have been some recent papers addressing that. So then I would refer to the work of Strominger, Raclario, and also Stieberger and Taylor. But yes, we expect that indeed this principal series where delta is 1 plus I times the real number is always playing a role. But you know, there has been all this question about how to deal with basically what is the right thing to look at, whether you want to include also the shadow primaries, the light transform, and all that. So it's under investigation. Yeah.
Because this delta just appeared as a number in your transform, right? Which could have been picked to be anything.
Yes, in principle, exactly. So in principle, yes. Thanks. I should clarify that. So the delta is arbitrary. Now, the statement about this delta lying on the principal series is really a statement that is coming from asking that the plane waves form a normalizable basis. So if you translate this statement, this is this translation of this statement in the Mellin transform basis that is telling you that delta lies on the principal series. But of course, we know that there are other objects which do not lie on the principal series. So with Sabrina Pastersky and Andrea Poon, we try to show that there is a sense in which you can analytically continue this delta to any value. Because you see, there is this translation symmetry is shifting delta by 1 already. Yeah. So it takes you off immediately. Even the usual translation takes you off of the principal series. Right. And the stress tensor obviously is not on the principal series either. So yeah.
I see. One more question. So the 4-point function, for example, is supported only on a particular slice of this cross ratio space, right? Namely Z equal to Z bar as a consequence of, I guess, translational symmetry in the bulk.
That's true. Yeah. So the 2 to 2 scattering, yeah, it forces you to the cross ratio is constrained to be eta equal eta bar or something.
So I guess the more general question is like these properties of these CFTs, have they been understood to some extent from bottom up, or that's going on?
If they have been understood from which perspective? Sorry?
From the bottom up perspective, like let's say, I mean, what kind of axioms that I should start with to get a CFT which is doing the job of producing scattering amplitudes.
Yeah, exactly. So this is what we call top down, rather, like, I would say that what we're doing is bottom up.
Oh, okay, like, sorry, yes.
Yeah, but that depends on if you're upside down. I don't know, but yeah, exactly. So it has been mostly done that. I think there have been some efforts, in trying to come up with a more intrinsic definition or toy model of celestial CFT, and that's precisely what I was listing here in the challenges ahead.
Yes. Okay. Thank you.
Yeah.
Thank you. We have 2 more minutes. Amitabh, you can go ahead.
Hey, Laura, thank you for the nice talk. So on this last slide and the last comment, you mentioned about black hole software and conservation laws. So you do mention about the super translation conservation laws. But what about these W symmetries? You expect W symmetries to be also realized in these black hole space-times, and conservation laws for these W symmetries will also involve contributions from the horizon. What is your view?
Yeah, I would say that whatever, that the black hole will not have a choice. You put it in the space-time, it will have to he cannot violate the conservation. Well, he will change because of this contribution from the horizon, but he will have to be consistent with all these symmetries, whether he wants it or not. So since this infinite W1 plus infinity algebra shows up, I mean, I expect it will play a role. To how precisely, I don't know. I would like to know. I mean, I'm working to try to understand how, this is the big picture of how these two programs, you've been also working on this software and charges at the horizon will contribute, and how to make all these two pictures one.